Hi. Yeah, I'm Siddharth. I also go by Sid. I will be talking about formalizing eight-dimensional sphere packing in Lean. We'll get to the maths in due course, but I want to first give a little bit of background on what formalization is. And I'm sure this is a buzzword at CMU that's sitting in my kingdom. And yeah. We have some idea of what this is, but for the course of this talk. So I'll talk about what it means to formalize fields medal in mathematics. And the background for this is that the solution to the sphere packing problem at dimension 8 by Maryna Viazovska won her the fields medal in 2022. So this is indeed this is indeed an accurate title for that section. I'll talk a little bit about what her solution actually entails mathematically. And then I'll talk a little bit about some of the intricacies that tend to come up when formalizing this in Lean. The key challenge is actually contour integration. And then we also have some stuff about general computational hurdles when working formally. Okay, so what is it? Yeah.
Should we see if we can dim the lights and
board?
Absolutely.
Yeah.
Is this better? Maybe
There's another
more?
one. There's another one. Tiny thing.
Yeah. This
There.
one,
Okay, maybe I'll get the back ones on. Is this good?
Yeah, you can turn the middle one on too. It's only the ones on the board.
I see. Sorry. Okay. Cool. Let me know if you want something different.
Yeah. Okay. Yeah, I should probably have started with that. Can everyone see, everyone hear, and all of that? Yeah. If at any point I'm not speaking loud enough, then let me know. Or if you can't see something, we can work that out. Okay. So what does it mean to formalize fields medal winning mathematics? Well, what does it mean to formalize any mathematics field? So formalizing mathematics typically involves expressing it in computer code. There are many interactive theorem provers out there. There are many programming languages in which you can express mathematical ideas, and then they check these ideas, they check your proofs down to the foundations that they are endowed with, and they check that they are correct. So there are many such languages, Lean, Isabel, Agda. You'll find many people in the philosophy department who work on one or more of these. I'm sure there's people in this department, in the computer science department as well, who are interested in this stuff. And the main advantage is that you can have a lot of confidence in the correctness of something that's been completely formalized. You may not have as much confidence in something that hasn't been completely formalized because the missing bit might be false. But if something has been completely formalized, then you can be pretty sure that it's true, as long as you trust the language. And languages like Lean, Isabel, and Agda are widely trusted. So I trust them, and I encourage you to as well. There are a few more advantages than simply, there are some advantages that really come from this. There's standardization and centralization, right? So when we talk about wanting to have all of mathematics expressed somewhere where you can just easily refer to it, well, there are many textbooks out there, there are many journals out there, there are umpteen libraries where you can go and find these resources, but you're not always confident. You might not always be confident in what you read because there might be details missing, there might be typos, there might be just obscure references to papers that can no longer be found anywhere on Earth. And an advantage of having all of this on a digital repository is that, first of all, it's all in one place, and moreover, you can be completely confident that whatever's on there is correct because it's been checked by a compiler that you trust. This also makes it faster review processes. There was recently, I think last year or something, there was a conjecture of, I think the paper is called On a Conjecture of Marton by Green, Gowers, Manners, and Terence Tao, and a couple of other people. And they actually formalized this in Lean in just 3 weeks. And this was even before they had submitted their paper. It appeared in the Annals in March, I think. And the point is that this was actually completely formalized before it was published. So I don't know what went on with people actually reviewing this paper, but I'm sure that this would have inspired some confidence in the reviewers. There's also proof discovery, which is that a lot of the times when you're formalizing something with a certain amount of generality, you try and think about, well, if I want to put this in the library, maybe I want it in more generality. Maybe I want something, maybe I want a different proof. Maybe the current proof is too it's not conducive to formalization. It's not very nice. And in situations like this, working on formalization can actually lead to the discovery of new proofs or the discovery of new theorems. Or you might say that, okay, maybe a certain definition is too specific. Maybe I can remove certain assumptions and then I define a completely new mathematical object on which I can prove theorems and so on. So it does also lead to mathematical discovery, genuine mathematical discovery. And we're seeing this more and more in the formalization space. And these are just applications to maths itself. There are plenty of applications to industry. There's also a lot of interest recently in using interactive theorem provers in teaching. So this is a very happening space. And as an example, this is how, in Lean, you always have this thing on the right called the info view, which gives you an example of which gives you a tactic state. So that's what it says here on top, tactic state. It tells you what variables you have and what your goal is. And this is a genuine, so this actually does appear, this exact tactic state does appear in a proof in my project. So this is a screenshot from VS Code. You can see that, so it gives you sort of the data that you have available. You have a natural number here, you have a Schwartz function here. It also gives you some assumptions that you can use. You have an assumption that f is not identically 0. You have this assumption that the real part of that the Fourier transform is real, and you have some assumptions there. So you can use all of these and only these to prove the goal. So this is how a tactic state typically looks, and you write code that then translates those assumptions into things that get you closer to the conclusion. Why formalize this particular result? Well, so a lot of you might have heard of Tom Hales. He's I don't know if he's retired yet. I think he told me in March that he was planning to retire soon. He's at University of Pittsburgh, and he famously formalized Kepler's conjecture, which is three-dimensional sphere packing. And he wrote something very interesting about his motivations. He said that he actually views formal methods as fundamental to the long-term growth of mathematics. And he spoke of these far more complex motivations than merely removing doubt from referees. And really, it is in the spirit of these more complex motivations that this project was undertaken. Because this is because the proof of Viazovska's solution to this sphere packing problem has been sort of there are a lot of very, very eminent figures who have read this proof. There are a lot of people who have said a lot of things about this proof. She won the most prestigious award in mathematics for this solution. So I think we can all be reasonably confident in its validity. But there's sort of these more complex motivations for wanting to formalize it than merely checking that it is absolutely 100% correct. So, well, I mean, you solidify the credibility of not just this result, but there are a few that build on it. There are a few results that, so essentially one of the things that this solution actually led to was an exploration of a more nuanced intersection between modular forms and the construction of these so-called radial Schwartz functions. And that's an area that I think Viazovska and some of her collaborators have since explored, and there's some more results that on this sort of more general theory of magic functions, such as universal optimality, such things. So this would lay the foundations for potentially verifying those as well. More than that, really in an age where interactive theorem proving is sort of becoming more and more part of a bigger and bigger part of mainstream mathematics, benchmarking becomes extremely important. And one question that we want to ask ourselves is, are we currently good enough to be able to formalize this? Do we need to do all of it by hand? Can we do some of it using machines? And really, if we want to test the capabilities of something like this, we need something modern. We need something that revolutionized its field. And really, this result is a perfect example. And finally, of course, it expands existing code. It expands theory on, well, there was absolutely nothing about sphere packings in MATLAB. I think there still isn't. I have yet to PR some of my things, which is bad on me. But there is a lot of general stuff that we've developed that I think can go into the library and at some point will go into the library, as well as methodology. So I'll talk a little bit about a rather surprising thing that came out of our project, which was a tactic, which is currently being PR'd to MATLAB. So I'll talk about these things. And formalizing something like this would be a huge breakthrough for the theorem proving community in particular. because it would mean that we are indeed in a position where we can do something like this. We are currently, I mean, we don't know if we are good enough. I think we are, because this is an ongoing project, but yeah, this would be a real test for what we can and cannot do at the moment. Okay, so well, who's working on this? What's actually happening? First and foremost, we have a website. It's always nice when you have a website. You can scan this QR code to visit that website. And there are many links here that you can follow to get an idea of what we're doing and where it's at. We have, for example, a dependency graph. If you click on the dependency graph, you can actually see what's been formalized, what hasn't been formalized, what definitions exist, what statements of theorems exist, but for what theorems do we have the statement but not the proof, stuff like that. So this is a one-stop shop. This website is a one-stop shop for everything about this project. You can find the GitHub repository, you can find the blueprint where there's a mathematical overview of the proof. The blueprint, by the way, the first version of it was written by Viazovska herself, and it's since been edited by all of us collaborators. And this is all of us who are working on it. Of these people, Chris, myself, Bhavik, and Siu are maintaining this project. So we're the ones who will review any contributions that are made by open source contributors from the Lean community. Yeah, so in March 2024, so the background is I did an exchange program at EPFL, the academic year 2023-2024. I did a 4-year integrated master's at Imperial College London. That's how I learned Lean. I met Kevin Gosler, and he introduced me to Lean. The story of most people who learn Lean in London. Yeah. So Viazovska and I kickstarted this project in March 2024. And between July and September, Gareth and I worked on formalizing sphere packing theory. We developed the theory of sphere packing density. We developed all of these ideas and sort of lemmas that make it easier to compute the density of the sphere packing, especially for periodic packing, because there's some simplifications there. I also worked on formalizing an important dependency that I will talk about in a moment. And then Chris and Siu, so they're modular forms. So Chris Bergbeck is currently faculty at the University of East Anglia in the UK, and Siu is a PhD student at Berkeley. And they're both sort of very interested in modular forms, even for their sort of non-formalization research. And Siu in particular, well, one of the reasons why Siu was involved in this project is because there's one part of the proof for which Siu came up with a different proof from Viazovska, a proof that we think is more conducive to formalization. And in particular, his paper is still being reviewed. So this is, sort of similar to, at least in terms of timeline motivation, similar to what Hale said about formalizing Kepler. So Siu and Chris are working on modular forms. From October to June, I worked on constructing the so-called magic function. I will talk about all of these things, but I worked on a very important chunk of this project for my master's thesis. So the contents of my master's thesis are precisely, well, first an exposition of the mathematics, and second, an overview of the effort that has gone in so far into formalizing that construction. So my supervisor was Bhavik Mehta. And Chris and Siu continued formalizing results on modular forms and quasi-modular forms. And the biggest sort of milestone moment was in Cambridge at the Isaac Newton Institute in June. There was a huge event called Big Proof, and Viazovska finally unveiled this project to the public. So we had been working closed source up until June 2025. That means that we'd been doing all of the sort of our repository was private. People couldn't see what code we'd written. They knew that we were working on this, but they didn't know what we'd done. And as of June now, not only can everyone see what we've done, but anyone with an interest can contribute to this project as well. It's now open source, which is exactly how a lot of these Lean projects usually go. So one of the reasons why I'm giving this talk right now is because I shamelessly want to advertise this project and get people to work on it. So if you're interested, let me know. Okay, so now I'll talk about the mathematics of the proof. Again, this is, bear in mind, we have limited time, so I'm going to try and I'm going to prioritize intuition over detail. The point being that there is a repository full of ultra formal stuff which has nothing but details. So if you really want the details, go there or talk to me afterwards. Okay, so the sphere packing problem asks the following question. I'm sure you know what question it asks. What is the densest arrangement of spheres, of non-overlapping spheres in Rn? Well, in R2, in R, this just looks like sort of intervals, right? You can just take the unit interval, take many copies of it, and that's good enough. In R2, it looks like sort of these sort of triangular arrangements. You take two circles and you fit something in the gap between the two. In R3, it looks like sort of tetrahedra or whatever, but you can't in general stack sphere packings from Rn. If I have an optimal sphere packing in Rn, it is not in general true that the optimal one in Rn plus one can be obtained by stacking it on top of each other in some sense. This fails very quickly, which is why this problem is very difficult and has not been solved for a general n. Yeah.
Can you just say what densest mean?
So I actually don't define density properly in this presentation. You can intuitively just think of it as if I have a bounded region, what proportion of that region am I filling? That's something called the bounded density, and then you take a ellipso as the size the region gets larger and larger. That's the density. Intuitively, it means how much of a bounded region is covered by, how much of any bounded region is covered by these spheres.
So I'm confused, like you gave us an example of an arrangement in at least R2, R3, like, putting balls on the vertices of a simplex, and you're saying that's not the densest for Rn?
No, not in general. Yeah, I think you can, I don't think anyone knows what the densest one is in, nobody knows what the densest one is in R4, but I think you can show that it's possible to improve any stacking of sort of the optimal, well, there's more than one optimal three-dimensional one. They locally look the same, but globally they are different. And I think you can show that if you stack these, you don't get something optimal. I think you can show that it can be improved. Or why, I think there's a paper that definitely does this that shows that this approach definitely fails by the time you hit n equals 10. I don't know if it deals with n equals 4 specifically, but it's not in general true.
What are the densest arrangements for R3 then?
They go by a couple of different names. I think one is called the face-centered cubic packing or something. So the idea really is, if I can, I don't have pictures of this. I probably should have done that. It's like if I have, this is a very bad drawing, but if I have something like this and I have a gap here, right? If I fill up this gap, well, I think this is too large to fill up these ones, but you can fill up another one here. I mean, it's essentially you just take this arrangement and then you stack it on top of itself by filling in whatever gaps you can, and you stack that on top of it and so on. And that gives you an optimal arrangement. But you can also sort of stack them in, there are different configurations. So you can sort of do different alternations of stackings and you get different global packings, but they locally look the same. I don't remember what it's called. There's a term.
You've got hexagonal close packing and cubic close pack.
Yeah, I think yeah. That's in that sounds right.
And cubic close packing is also known as face-centered cubic.
That's the term I know. Yeah, face-centered cubic. Yeah.
So it's also you can also get it. It's called face-centered because you think of an infinite grid of cubes, and you put balls on the faces and make them big enough so that they touch. So it has tetrahedral and octahedral holes.
Yeah, so that's the reason why you can't just sort of solve it in Rn by some kind of recursive argument. Anyway, so she showed, Viazovska, that it corresponds in 8 dimensions to the sphere packing with sort of sphere centered at points on the E8 lattice. And well, what is the E8 lattice? There is, well, I'm not going to go into too much detail here because, well, I can say a lot about E8. I can talk about Lie algebras and root systems because I am interested in that stuff, but I won't. Instead, what I will mention is that you can simply think of it as a set of vectors in R8. There is an E8 root basis, which is a special basis in R8. And you can just extend that to a lattice. You can take the Z span of it. That gives you a lattice. And in fact, what this illustration tells you is, so in this illustration in particular, what's happening is that you look at things in the E8 root system. The E8 root system is a set of vectors that's larger than just the basis that I mentioned. And what you do is you project all of these onto a plane. And so the vertices here are vectors in E8, and the edges connect nearest neighbors. So you can see by just how connected this graph is that the vectors in the root system are pretty close to each other. So that can give you some intuition for the fact that this is indeed a dense packing. And it was suspected for a long time that this was the densest packing in R8, but it was only shown in 2017 by Viazovska. Cohen and Elke suggested a method in 2003 to come up with sort of these so-called magic functions that'll let you prove optimality of such things. And when they came up with it, they thought they'd solve the problem, but unfortunately they hadn't, and it took several more years of trying. But we'll go over this now. Constructing such functions is extremely difficult. Okay, and Viazovska's breakthrough was to construct. So what they showed is that if you have a certain function with some special properties, then all sphere packings are bounded above by some upper bound, which is given in terms of that function. So then if you find the right function, you find the right upper bound. And if you can show that that upper bound is achieved, you show that you have optimality. I'll go over this in more detail, but the breakthrough is that she constructed such a function using modular forms. So Cohen and Elke proved the following. So if f from Rd to R is a Schwartz function, it's not identically zero, satisfies this 1, 2, and 3, then the densities of all sphere packings are bounded about by this quantity, which is expressed in terms of f. F hat is its Fourier transform here, and the volume of a ball in dimension d of radius 1/2. And if f satisfies these conditions, and if this upper bound that you see over here is precisely the upper bound of some, is precisely the density of some known sphere packing, then that means that if the densities of every single sphere packing are all less than the density of some known packing, then that means that that packing is optimal. Right? It means that the upper bound is achieved by that packing. And thus far, magic functions have only been found in dimensions 8 and 24 using this method of modular forms. So Viazovska constructed in dimension 8, and then soon afterwards, along with Cohn, Kumar, Miller,
Maybe there's also magic functions for dimensions 1 and 2.
So it is believed that they exist. That was the next one. I didn't include 1 in this list. I think that would be a little, so it is. I don't know if they've actually found an explicit one in dimension 2. But I think I spoke to Viazovska a few months ago. She said she's very sure that one exists. So I'll believe her. Okay. So I've mentioned a bunch of conditions, and I'll talk a little bit about what these conditions actually tell you. So first, what are Schwartz functions? I think in a department filled with as many analysts as this one's, this is probably not as new to most of the people in this room as it was to me when I first encountered it. Well, essentially, they're smooth and rapidly decaying functions. They're functions that decay faster than any sort of inverse power of the norm. So they're faster than polynomial functions. The function and all its derivatives are faster than polynomial decay. We can make a few observations. First of all, set of Rd to R Schwartz functions is an R vector space. Not only that, but the Fourier transform is a linear operator on this space. It's a linear isomorphism on this space. And finally, you can show that if I have a Schwartz space, and then the map that takes, so the map that goes from this Schwartz space to another Schwartz space obtained by composing with a function satisfying some growth conditions, you can show that that is also a linear map of Schwartz spaces, which comes up in the project a few times, because you want to essentially build bridges from R to R Schwartz function. You want to turn R to R Schwartz functions into Rd to R Schwartz functions, and to do that, you compose with inclusions and so on. Okay, so dependencies. So I'll talk about some of the dependencies of this result, whether they've been formalized or not. The first one is that when I say that the densities of all sphere packings in R are bounded above by this, the proof only shows that the densities of all periodic sphere packings are bounded above by this. If you read Cohn and Elke's Kohn-Elke's original paper. There's one line at the top of the proof that says it is enough to consider periodic packing, see the appendix. And that's how it goes. So this is something that's currently being worked on. I couldn't find the right accent there on top of the E. It should be a tréma. So this is a friend of mine called Yale who's working on this.
I think it's a backslash double quote.
Might be, yeah, for the future. But yeah, that should be a tréma, not a, I don't know what that is. So this is being worked on by Yale. And then there's also the Poisson summation formula in Rn. So this is an important dependency of this. So if lambda is a lattice and you have a Schwartz function, you have this summation formula, which essentially relates the sum of the function to the sum of its Fourier transform along with a factor over there and a scale factor. And this is something that we have in MATLAB only if lambda is the integers and d is 1. So we want to generalize this by some inductive argument. I have a proof path in mind, but it's not as easy as it looks to actually formalize this. It's also not that easy to find a formalization friendly reference. Like Serre says something about this, but it's not. But it's not. There's not as much detail as there would need to be if we wanted to formalize this. So I definitely need help with this. I have a proof path in mind. If you want to do something, read and you know a little bit about this stuff, then let me know, and we can work on it. Okay, so these are the dependencies of Kohn-Elke's that still need to be that for which there's still work being done. I managed to show that given these, I've managed to prove this. Given these, as well as given some convergence results of infinite sums, very few are remaining. Actually, someone proved some of them a while ago. But given that, so that implies this is pretty clear. At least in lean, it's pretty. Yeah, I have it formally that implies this. Okay, now, well, what does the theorem really tell us? What are the insights it gives us that make it easier for us to find a magic function? Well, first of all, it tells us that it's enough to restrict our search to radial Schwartz functions, because if you observe these conditions, they're only really stated in terms of, so this one involves only the norm. It doesn't really involve anything else about x. So if I look for a radial function, I don't break anything. So it's actually nicer to look for radial functions because it makes it, because first of all, it allows us to consider R2R Schwartz functions. And then by composing with the norm, you can show that you then get an RD to R Schwartz function. So if I have a Schwartz function from R to R and then I compose with the norm, provided my R to R Schwartz function has derivative 0 at 0, if I compose with the norm, I still get a Schwartz function from Rn to R. And this is, I have a semi-complete proof of this in lean. So again, I need some help with that as well. Well, not only that, the reason why it's useful to look at radial Schwartz functions is not only that, but also you can sort of break a radial Schwartz function up into a +1 Fourier eigenfunction and -1 Fourier eigenfunction. So the point is, I've kind of abused notation here, but the point is the Fourier transform of this is itself, Fourier transform of that is minus itself. You can restrict. So then the game becomes, can I find Fourier eigenfunctions, Fourier plus and -1 eigenfunctions, which obey these conditions that I can just put back together in some form to get an optimal function. And the second insight that this gives us is that, well, the function that you want, so again, when I say double zeros, I'm considering this guy now. Such a function would need to have double zeros, so not just a 0 at any length corresponding to a lattice point, but really a double 0 at most of them. And the reason why you'd need a double 0. So first of all, you can inspect the proof of Kohn-Elke's, and this is maybe a mysterious thing to put in here because I've not given you the proof of Kohn-Elke's, nor will I. But you can just, I hope you'll believe me when I say that you can inspect the proof and see that you need to have, an optimal function needs to be 0 at any lattice point. And double zeros follows from, well, it really follows from this fact here, right? Which is that you're 0 at some point, and then you hit a 0, and then you somehow stay negative, which means that you go up to 0 and then you have to stay negative. So this and you know that you're smooth and so on, so you can conclude that you have double zeros. And therefore, what we really need is Fourier eigenfunctions with double zeros at lattice points, which is exactly the title of section 4 of Viazovska's paper, which is also the bit that I worked on formalizing for my master's project. Okay. So, and if anyone has any questions at any point, please just, yeah, interrupt me, it's fine. Okay, so anyway, so Viazovska constructed a radial Schwartz function with these properties as a linear combination of Fourier eigenfunctions called A and B for plus and minus one eigenfunctions, and then she scaled it to obtain this. I'm going to mention the definitions of these guys. They're long, they're messy. You don't need to know what these are. And I'm in all of the arguments that I go through for the remainder of this talk, the only picture that you will really have to have in mind is this one. So what is going on here? So, well, I have a Fourier, I claim that this is a plus one eigenfunction, this is a minus one eigenfunction. I've not defined these functions. I'll talk a little bit about them, but I won't define them. Really what's happening here is that in these functions, so you have one integral here, which is an integral along this contour or some other contour. And I'll talk about why these contours have been chosen in particular. They might seem a little unnatural as opposed to like circular contours or something. But the point is that you have an integral going from minus one to I. Over here, you have an integral going from 1 to I. Over here, you have an integral going from, well, there's a negative here, so it's really going from I to 0. And you have an integral here going from I to I infinity. And these are integrals in terms of some complex variable z. So these are integral transforms of some variable x, which is an 8-dimensional vector. So really, you can also view these guys as sort of, wherever I've written norm of x, you can also replace that with an r, and then you view it as an R to R Schwartz function that you're just composing with the norm to get an R8 to R Schwartz function. This is what I alluded to earlier when I said it's not, that's the power of looking at radial Schwartz functions, because computing derivatives in R is much easier than computing Jacobians in R8. So this is why this is one of the reasons why it's simplification. So anyway, given these functions A and B, you can obtain a magic function G. Well, I suppose technically magic function is a scaling of G. But you can obtain this guy by doing some linear combination of A and B. You get these coefficients by inspecting the values of A and B at specific points. I'm not going to go into it. But really, that picture is the one that I want you to keep in mind. And we'll keep coming back to that to see, especially to investigate some of the challenges that arise when attempting to formalize this construction in Lean. Because contour integration turns out not to be as easy as you might think. I mean, I find it difficult even to do on paper, but that's just me. Anyway. So what are these functions phi naught and psi s? Well, they're defined in terms of modular forms. And I'm, again, going to only provide some intuition for what modular forms are. So modular forms are essentially holomorphic functions from the upper half plane to the complexes, which satisfy some change of variable properties. They also have some boundedness property, or well, holomorphicity at I infinity is what you say, which is not very relevant for what I'm going to say, or how I'm going to show that they're useful to this project. So I'm not going to talk about holomorphicity at I infinity. But the point is that a modular form satisfies some invariance property, some weighted invariance property under these Möbius transformations. So this is what you would want, for example, a weight for level 1 modular form to satisfy. So there are two words here, right? There's the word weight, and there's the word level. Well, what level tells you is that I can really consider any matrix in SL2Z, whereas if the weight, if the level were 2 or the level were 3, then I would also need to have some mod 2 or mod 3 or mod m congruence relation on the subgroup of, on some subgroup of SL2Z that I consider for this kind of for this kind of definition. The weight is this number here. So weight 4 means that I want this function alpha to satisfy. So I take this bottom row of this Möbius transformation CZ plus D, and I raise that to the -4th power. And when I multiply that, I get back what I started with. Okay, and well, you'd want, so the point, so why this is relevant to us is because at some point, we'll end up, we had a whole bunch of integrals, right? And something that they teach you in first year calculus is that when you have integrals, sometimes you can change variables. And changing variables becomes an extremely common theme in this proof. So the point is that when you have some invariance properties under these changes of variables, it makes it easier to show the eigenfunction property, to show that the +1 eigenfunction, when you take the Fourier transform and then you do some change of variables, you get back the original function. I'll talk about, I'm going to do that diagrammatically using just the contours, and then I think it'll be clearer. So for instance, if you consider the function psi s, which if we back up a little bit, this guy psi s was in the definition of the minus one eigenfunction. And this is not how it's defined in the paper, by the way. The minus one eigenfunction is defined a little differently in Viazovska's paper, but you can prove, because you have all of these myriad change of variable properties, you can prove that it looks like what I say it looks like. And the point is that you can show something like this. And this, yeah, so it endows them with these change of variable properties, which allows you to, actually, I think there's a minus sign missing here. But anyway, if you look at this, the point is that this allows you to change the integrand of one of them to the integrand of the other, which swaps some integrals around and lets you prove the eigenfunction property. So you have these kinds of invariance properties. So you get something called psi s, which has that property. If you define this function to be psi t, then psi t also has some change of variable property. So you have a whole bunch of these Möbius like invariance things, these weighted. So this is a sort of, you see an exponent of 2, you see an exponent of 2. So you have these weighted Möbius invariance properties that come up time and time again in this proof. And these are crucial to establish that. So recently we had a contribution from someone who's I think currently based in Heidelberg in Germany, who proved that, who proved a whole bunch of relations between some modular forms that are used in the definitions of psi s and phi naught. So phi naught and psi s are not themselves modular forms, but they are defined in terms of modular forms. And those definitions in terms of modular forms endow them with these change of variable properties. So the contributor proved a lot of relations between the modular forms that are used to define these guys. And those will then help us show, for example, this, which will eventually help us show that the Fourier transform of B is minus, that B is indeed a minus one Fourier eigenfunction. So I'll talk a little bit about contour integration. And really here, I think I've kind of bombarded you with a whole bunch of information. And I think here it'll become clear what some of the challenges are, as well as how some of that information is useful. So first, contour integration. So I mentioned that, well, if we back up to the definitions over here, we didn't specify a contour to go from -1 to I or to go from 1 to I. And I've kind of mysteriously put those rectangular contours there. Why have I chosen those contours? The first thing I'll mention is that these integrands are all holomorphic on the upper half plane because they are defined in terms of modular forms. In particular, there's also a modular form with denominator, which is non-vanishing, whatever. But the point is that the integrands are holomorphic, so I can move these contours around and the integral doesn't change. So why have I chosen that particular contour? In particular, there are two other contours that are worth considering. So this is maybe the most natural, right? In complex analysis, we always see circles. So this is somehow the most natural one to consider. I also strongly considered this one for a long time, just a straight line, because it's easier to parameterize and therefore it's easier to work with formally. But there are some caveats that come from working with this one. So the reason why we chose this one in particular is because we have the following theorem in MATLAB. So this is taken from MATLAB documentation. So what this says effectively is this gives you the Cauchy-Goursat theorem. The Cauchy-Goursat theorem is the theorem that allows you to sort of integrate a holomorphic function that's sort of continuous on the closure and sort of differentiable on the interior. If you integrate like that, or if you integrate on a complete circle, you get 0. And this is the Cauchy-Goursat theorem. And one of the versions of, so we have Cauchy-Goursat for complete circles, so not these quarter circular thing, but complete circles. And we have Cauchy-Goursat for rectangles. That's all we have Cauchy-Goursat for. We don't have Cauchy-Goursat for anything else. And which is a little bizarre when you think about it. But there are many reasons why we don't have it for, I don't know, it's just a difficult theorem to prove in complete generality. And that's why, I mean, I don't think you would need this, but we also don't have the Jordan curve theorem, which is notoriously difficult to prove as well. So Cauchy-Goursat for rectangles is the reason why we chose to go with rectangular contours. Now, a priori, it's not clear why we need to deform integrals or deform contours. So I'll talk about that. So remember how we said that the Fourier eigenfunctions need to have double zeros at lattice points? Well, really, how we show that, how Viazovska shows that, is she shows that this is another way of expressing A, and you have something very similar to, you have a similar alternate expression for B. Now, if you pay close attention to this, this looks like this, right? There's one integral which is just going from 0 to I infinity, right? Now what you do is you take this, and this has double zeros because it's sine squared, and you have your periodic whatever. So what you do is you take the sine squared, you express sine in terms of the exponential, and you break this integral apart. You do some like affine changes of variables, you break this integral apart, and you get something that looks like that. This looks like all of a sudden from just being one line, you have 3 lines that go like this, right? Now, if you recall the picture that we had earlier, if we want this to be equal to A, we want to show that it's equal to that. So what we want is somehow we want to just merge these onto this axis, and we want to sort of, so the way that you would do that is you would say, okay, well, let's consider this new contour now. I know that going along here is the same as going along here, because I have Cauchy-Gauss for rectangles, and same thing on the other side. I do that again. And I can just keep doing that because you can prove that the integrands, so this horizontal thing, you can prove that that vanishes. In particular for the integrand, as you go off to I infinity, you can prove, as the imaginary path goes to infinity, you can prove that it vanishes. So therefore, you can deform contours in this way. And this is extremely important because this is how you prove that this is equal to A of X. And that is how you sort of, well, I mean, the double zeros was technically, I shouldn't really call this the double zero property because that was a necessary condition, not a sufficient condition. But you can use this to then conclude that it satisfies the Cornell-Keys conditions. You need this alternate representation, and then you need to analytically continue this and so on. Yeah.
Would we pass going down as well to get the down in the middle picture?
Yeah, I didn't mention that. That's a good point. So what actually happens is that when you take these guys and when you push them onto the imaginary axis, you have one copy of this, one copy of this, and one copy of this. And well, they're all slightly different integrands. But the point is that when you add them all together, you again exploit one of the properties that comes from modular forms, and you can show that you get back precisely the integrand that you wanted for this one. So yeah, that's a good point. Yeah. So that's why we need rectangular contours. Now, there's something else that's very difficult, and this is something for which we actually don't have a clear answer. This is probably our biggest roadblock so far. So this is how the function, well, I'm only going to talk about the +1 eigenfunction. Really, it's the same for the -1 eigenfunction as well. I think these diagrams will apply to both, just with the minus sign in one case. So before taking the Fourier transform, we have something that looks like this. And I think the colors are not very clear on here, but these are all different colors. That's green, this is brown, that's red, and this is blue. And after you take the Fourier transform, what actually happens is these get moved around. Because we had that A of X was a sum of 4 integrals. You can show that each of those integrals is a Schwartz function in X. And then the Fourier transform was linear on Schwartz functions. You can distribute it over those ones. And then you can show that the Fourier transform of this one is that one, Fourier transform of this one is that one, and vice versa. And well, if the Fourier transform is simply permuting these things around, it's not changing their sum. So it's a Fourier eigenfunction. So that's how the eigenfunction property works. And in order to establish this, we need a rather non-trivial fact about complex integrals. We need to actually be able to go from these quarter circle things to rectangular things. And this is something that we don't have. And we don't have a good way of doing either. So we have Heather Macbeth and Alex Kontorovich are currently working on this. And I will see Heather next week and I will have a conversation about this. But yeah, it's quite a roadblock. So, okay, so before taking the Fourier transform, if I just look at this one, right? If I just look at this integral, this is one of the 4 things that adds up to give you the main thing. If I take this one, what happens is that you can show that the integrand is integrable and so on. So then you take a Fourier transform in X, then you get a double integral, you apply Fubini-Tornelli, and then you take the Fourier transform inside, you take the Fourier transform of the thing on the inside, and then you get the same contour in Z, because Z is not affected by this Fourier transform. Only X is affected by the Fourier transform. So why that contour is dashed is because the integrand is different. Okay, it's not the same integrand that I had earlier, but it's the same contour that I had earlier. Okay, what you then do is you want to essentially transform this contour into something that goes from 1 to I, right? You eventually want to end up here. So you have to transform that contour into something that goes from 1 to I. And at the same time, you want to do it in a way that gives you the same integrand So what you do is you apply Möbius transformation. You apply the Möbius transformation that takes that thing to this thing. And again, you don't know a priori that the integrands of this one and that one are the integrands that you want. But then you apply the magic of modular forms, and you can show that because you have so many invariance properties under these Möbius transformations, that the integrand that you get from doing this thing is the right integrand. So this is a solid one, meaning that it's the integrand of this one. And then we have to do some contour deformation where we say, well, we have something like this. What we want to do is we first want to do something like that. So we want to be able to deal with these kind of shapes. And once I have that, and that gives me this. So this is kind of, so really the roadblock is over here, because we have enough. I think we have just about enough to do the other ones. And we haven't yet done them, but I think we have enough to do them. Here, this bit is a little difficult. Not a little, it's extremely difficult. And we're quite stuck. So if any of you want to help with that, that's something I would love. Okay, lastly, I'm aware that we only have, I think, 10 more minutes. So I'm going to quickly talk about some of the challenges that come from doing computations in EU. First of all, are there any questions about everything that I've done so far? Yeah, go ahead.
The idea in the Maryna's proof, Maryna's paper, or just the difficulty in formalizing?
Well, both.
Okay.
Yeah, this is a key idea. This is a key idea in Maryna's proof, except, well, I think she doesn't really talk about it in too much detail because, in fact, I don't, as far as I can remember in the original paper, she didn't even, she maybe just mentioned that the integrands were holomorphic. I don't think she actually proved them, proved that they were holomorphic. But again, I think that's reasonable because, you know, they're defined in terms of holomorphic things. And well, holomorphic things and in the denominator non-vanishing and holomorphic things. But yeah, I mean, she doesn't really talk about these, how these changes of variables behave. Also, well, Maryna never actually specifies the contours. See, she just says -1 to 1, and then you do this change of variables. You're suddenly going, sorry, -1 to I, and then suddenly you're going from 1 to I, and she stops here. From here to here, this, well, I mean, in some sense, it's because we have made this choice to go rectangular. I think you're fine if you stay circular, but then you run into challenges with the sort of the infinite, sort of the unbounded contour deformation thing that we saw earlier. We had these three things that you wanted to sort of, so we run into problems over there. But either way, so suppose we were to redo everything that we've done so far using these quarter circular ones, then you would still need this exact shape to do the unbounded thing. At least if you wanted to do it the way that we have done it. Because there's no Cauchy-Gouza for, well, I mean, yeah, you can't avoid this, I think, is the conclusion that I've come to. I've thought about this quite a bit, as have some of the others working on this project. I don't see a great way of avoiding it. If not in this proof, then in different proof. But again, yeah, if any of you have any thoughts or ideas, please, I'm absolutely open to that. Okay, any more questions? If not, I'll talk a little bit about some of the things that we've accomplished on the computational side of things. Okay, so okay, if you'll forgive the horrible wordplay here, the point is simply that we're doing all of these. Well, when I say computation, it's not in a numerical sense. It is in a formal sense, and that's why it's difficult. It's because this proof is full of sums. It's full of products. You know, modular forms in general are full of infinite products, and we deal in particular with this modular form known as the discriminant form. And the discriminant form has this well-known product formula. You can express it as a certain infinite product, and then you need that product converges, and you need stuff about that product. So just convergence in general is not as straightforward as you might think, and you need to carry it around a lot, because naturally there are some things that you can only do if you have convergent things. So in general, it's quite difficult to do computations in Meeting. And I want to talk a little bit about some of the things that we've done to simplify this process. So first, we actually wrote something called a tactic as part of this project, which essentially does certain things automatically. So metaprogramming is the science of writing tactics. I think that there are probably people here who are way better at metaprogramming than me and who know more about it than I do, who will probably come up to me afterwards and say that was oversimplified definition. But regardless, computations in Lean are difficult, and we have some tactics that help us do these automatically. So we have something called SIMP, stands for simplify, field simp, simplifying a field, nom-num, normalize and simplify numerals. And nom-num is the one that I want to focus on here, because things like that, these are all considered numerals. Okay, I suppose it's a bit ambiguous, like what really is a numeral? I think looking at the meta code, it looks like, because we don't actually use the word numeral. I think looking at the meta code, what we talk about is something like injections from the naturals into semi-rings and things that build on those, something like that. But for example, something like pi, which is transcendental over q, is not considered a numeral. I is not considered a numeral either, even though it's not transcendental. It's not considered a numeral, and it's treated as a symbol rather than as a number by nom-num, or at least that's how it used to be. So what we did was, well, a lot of the times when you want to prove that some converges, or when you want to prove something, there was a situation. So the reason why this tactic even came up is because Heather Macbeth, who's a very prominent figure in the formalization community, she joined Imperial College last year, and she ran a metaprogramming seminar there, where she was teaching us how to write tactics. These are the basics of how to write tactics. And at some point, she saw me working on a proof for this project, and she saw that I had proved that 1 plus I is not equal to 0, like 3 different times. Of course, I had just copy pasted the same proof, but it was a 3 or 4 line proof. And she said, oh, I can probably do that in 1 line. And turns out she wasn't able to do it in 1 line. So she said, well, I really should be able to do that in 1 line. And I agreed, as did a couple of the others there. So Heather, myself, and this other master's student, who's now a PhD student at the London School of Geometry and Number Theory, the 3 of us collaborated and wrote this tactic. So the idea is that if an expression is made up of several complex variables, several complex numbers, and I know that the real part and the imaginary parts of those complex numbers are all numerals, then in theory, I can, well, not just in theory, as we can see, we turn that theory into something practical, where you can just look at the real part, look at the imaginary part, you can simplify those, and you can put them back together, right? It sounds pretty logical, and that's what we did. So for example, we know that this is, I think, yeah, this is true. I haven't messed up the computation as far as I know, which is entirely possible, by the way. So this can be simplified by nom-num. So these bits, well, it can simplify this to 0 times something. So it can simplify that and simplify that. But you really want to be able to split it up into real imaginary parts. So this was, again, I'm sure that someone who's better at Lean than I am can maybe do this in a few steps, in like fewer lines. I did also split this up a little bit because I wanted to illustrate this is that there's a couple of non-trivial things happening here. Such as, for example, in this step, really all that's happening is that you're showing the conjugate of that is this. And then here you're doing, so ring NF is something that normalizes expressions in rings. It puts them in a certain form. And then you simplify it, and then you casts are inclusions from sort of like the rationals to the reals would be a cast, for example. So you have a couple of these things. And this is how it used to look. This is how it looks now. So nom-num didn't used to be able to do this, but we wrote something that extends nom-num and sort of gives it this new magic power to be able to work with these kinds of expressions. And yeah, this was jointly done with Heather Macbeth and Edison G. So this is now a pull request on GitHub. Admittedly, I haven't worked on the pull request as much as Edison has. And really, it was Heather who wrote some skeleton code and got us to fill it in as an exercise in metaprogramming. And then it was a very instructive exercise. And then we met a couple of other people. They gave us all kinds of feedback. We implemented that. Yeah, it was great. So at Cambridge, there was this workshop that we went to, and we'd all gone for dinner. And then all of a sudden, Edison just, like, we'd hardly been sitting for 5 minutes when Edison whipped out his laptop and we started working. So it's fantastic. Yeah. And yeah, so there's one final thing that I'll mention because I'm nearly out of time. I mentioned that we have to deal with these things like convergence of infinite sums, convergence of products, and integrals, and so on. So that's actually even harder and even more sort of that's an even bigger problem for this particular project because we just see so much more of that. than we do of like just computations of complex numbers. So the biggest challenge is that you have to carry around these compatibility things. Like we have something called summability, which is absolute convergence of sums. Technically not. Technically, it's defined as convergence of a sum in every rearrangement, because what is an absolute value in a more general setting? So that's how summability is defined. And multipliability is defined in exactly the same way. You have an infinite product and you have all rearrangements of it should converge as well. And if that is the case, you say that it's multipliable. But in complex analysis, typically you would want absolute convergence of products to be the absolute convergence of the sequence of logs or something like that. That's what you'd really want. And you don't have that in the lean definition. So you are allowed to converge to zero, whereas typically you would diverge to zero. Like something like the constant sequence 1 over e, for example, right? The sequence of logs, that's going to blow up, right? Whereas if you take an infinite product of just 1 over e, that goes to zero. And typically you'd not want to allow this in theorems that have an if and only if condition involving absolute convergence of an infinite product. So I actually worked on improving the theory of infinite products in lean, and in particular, improving some of the theory of these sort of defining the absolute convergence of an infinite product of complex numbers to be sort of absolute convergence of the sequence of logs. And I did work on some theory over there, and it's not, well, there is some debate as to whether it's really relevant to MATLAB or not, because this only gives you sort of one direction of certain if and only if statements. This is strictly weaker than absolute convergence of infinite products. Anyway, so then there's integrability as well. So that means that the integral is finite and your function is almost everywhere strongly measurable. And I actually don't know what almost everywhere strongly measurable is, because you never encounter it in practice. At least I've only ever dealt with, I think I've mostly dealt with smooth functions, occasionally with, well, I definitely always have measurability or continuity or something that implies measurability. And measurability implies this. So not satisfying these doesn't give you an error, and that's really the thing that makes it really difficult to work with these. Because if the assumptions aren't satisfied, then an expression involving a sum or a product gives you a junk value. So if I write out a sum of something that's not summable, then that's zero by definition. If I write out a product of something that's not multipliable, that's 1. If I write out an integral of something that's not integrable, I get 0 again. And these are not errors, right? These are just junk values that it gives you. And this means that sometimes it's difficult to keep track of whether you've done things right or wrong. So unless one is careful, one may not realize that something is wrong. So you can instead deal with stronger versions of this. You have something called has sum, which is a stronger statement. But this always needs to sort of, if you're exclusively working with has sums, then you always have to carry around these convergence results. And in particular, if you have a slight modification of the thing you're summing, you have to also provide new proof that that thing converges and so on. So the caveat is that this requires a lot of carrying things around. And actually, the workaround is that you can use this and you only prove convergence where you know that you need something that's not a junk value. So the reason, so I asked myself the question, so when I was first working with infinite sums and products and integrals, I did wonder why they'd chosen this particular, they'd chosen to design it in this particular manner. But I think that the advantage is, for example, that when you want to prove the monotonicity of non-negative integrals, typically, in the lean library, if you want to prove, well, if you want to use the monotonicity of the integral, if you want to say that f is less than or equal to g almost everywhere, then the integral of f is less than or equal to the integral of g. You need both f and g to be integrable, because otherwise you might get a junk value for one. But if you know that f and g are both non-negative, then you only really need a convergence assumption on g, because you can just do cases on f and you say if f is not integrable, the integral is 0, so it's trivially less than or equal to the integral of something non-negative and so on. So you can simplify this, and in particular, I took great advantage of this sort of these junk values when it came to bounding integrals to prove Schwartz, because then you're bounding absolute values, you're non-negative, you can do a lot more things. I've reduced the proof from requiring sort of convergence of 3 integrals to convergence of just 1 integral, and then you can show that the others converge as well. So it is indeed possible to take advantage of the fact that these give you junk values to simplify matters. Okay, that's it for me. So questions?